Right, so logistics problem set will be due next week. Sorry for the confusion. I guess I had announced that it would be due at 2 p.m. Yesterday, and I think on the sheet it was due at 4 p.m. So if you got it in by 4 p.m., you're still good. Don't worry about it, but it really is due at 2 p.m. next week. Update on the reading. I haven't had a chance to do that yet. I'll post the reading for next week on the wiki tonight. So you'll have hopefully some lead time on that. Midterm number 2 is in 2 weeks from today. It's in class. Yeah, I know, it's crazy. It's just happening. It's in class, and I'll give you some more details about that next week. But essentially, it'll be the same sort of format. It'll be vastly easier. No, it won't be vastly easier, but maybe we'll calibrate a little bit to make you guys all feel a little bit better. But it's all great on a curve, so it's all relative pain. Office hours for me will be normal next week. Colloquium today, Mariska Creek from Harvard is going to be speaking about high redshift galaxies. And in particular, she's going to be talking about the relationship of different properties of galaxies with other properties of those same galaxies. And what's interesting is we know a lot about those relationships, as we'll see starting next week, in our own galaxy. But we don't really know the evolution of those relationships as a function of cosmic time. So that's something that she's on the forefront of and is been working on for a number of years. So that's at 4 p.m. today in number 1 LeConte. Some of you have been asking about the extra credit project. Again, we'll give you more details on that. Probably not next week, but the week after, because the GSIs and I have to talk about the parameters. But it will be due May 5th. It's purely optional. It will only help your grade. And as I said at the beginning of this course, because we're interested in you as proto-researchers, we're interested in motivating you to do some sort of research that interests you. So writing up something on a topic of interest that's related to this class is more or less what you should be considering doing. There's many different ways to do that. And in the past, we've had somebody write some sort of online web page thing that actually solves the Freeman equation under different conditions. That's a sort of thing we'll do in cosmology. They've looked at alternative versions to general relativity and sort of research what that could how it could manifest itself on different scales in a way that we could actually observe. They've looked at black holes. So you kind of have to think about what interests you most, and one of the reasons why we do this at the end of the class, of course, is that I want you to have seen a large part of the cosmology before you start working on this. We've had people rewrite Wikipedia articles that were wrong, blah, blah, blah. So it's fairly far-ranging, but if you're already starting to think about a topic that interests you, once we tell you exactly the parameters of the extra credit project, we'll be asking you to actually come up to us and sort of get your nominal project idea vetted so that we can give you the green light. Any questions on logistics? Okay. So last time with Jonathan, you talked about the Strömgren sphere. And remember, that was a distance within an H2 region where you had a perfect balancing of the recombination rate and the ionization rate from a blue and UV bright star. You looked at the galaxy, the Milky Way, and looked at some of the structures within the Milky Way and got an overall sense of scale. And one of the very important things to remember is that we believe that the sun is 8.0 kiloparsecs away from the galactic center. And we believe that we're moving in roughly a circular orbit around the galaxy with roughly a velocity of 225 kilometers a second. This number sort of bounces up and down a little bit every few years. People make a more accurate measurement, or they identify systematics that said other people's measurements were wrong. And this 8.0 number is sort of today's best bet, but it could go to 8.1 or go to 7.9. But that's roughly the right answer. If you take these two numbers and you just assume circular orbit, you can come up with a time scale for how fast the sun is moving around the Milky Way, and you come up with something like 2.5 times 10 to the 8 years. So 250 million years is the period of the sun around the Milky Way. I think you talked about metallicity. I'm going to keep looking back at Jonathan, make sure you're saying yes. Remember that was usually denoted with this bracket notation. And here, this would be the metallicity as measured by iron versus hydrogen. Remember, hydrogen is this primordial material. Iron is something that's definitively made in supernova explosions and leading up to supernova explosions. This is defined as the log of the number of iron atoms divided by the number of hydrogen atoms minus the log of the number of iron atoms divided by the number of hydrogen atoms in the sun. So this is an interesting measurement, and that just has some value associated with it, and something that we think we can measure by taking very detailed looks at the spectrum of the sun. And this is something that we might want to infer in a distant star and try to understand what its metal enrichment history is and how old that star is. It's going to be correlated with its metallicity. A metallicity of 0 means that these two quantities are the same, so you're looking at a star that has the same metallicity as the sun. In theory, it should have been enriched at the same rate and at the same level as the sun. If this number is less than this number, that means that there's less iron. So lower metallicities less than 0 are ones that are less enriched, right? And remember that as you go from population 3 stars, which are these very, very sort of newly forming stars in the very distant universe. These are the first stars that form out of primordial material. Those wind up dying, expelling some of these waste products that winds up making themselves and those products into new stars, and that's how you get population 2. And then those stars will wind up dying, and then you get population 1. Remember, population 1 are the ones that typically inhabit the disk of the Milky Way. Population 2 are those that typically inhabit the halo of the Milky Way. Yes, question?
Everything that's not hydrogen material,
It's actually one of the easier elements to measure in spectra. But you can do this for any element. You could just call this X divided by H. And in fact, a lot of people do that. One of the difficulties is for a given spectrum, it's easy to sort of see characteristic lines that might tell you exactly how much of this stuff you actually have. But if you look at the same sort of thing at higher redshift, so this is where you have cosmological expansion and you're looking at galaxies, you're looking at aggregate numbers of stars, you want to know about the total metallicity of that galaxy, they may actually be different lines from different elements which are in your spectrum. So you actually might have to use a different line altogether. But it's a great question. Iron sort of makes the most sense because it's the thing that you really can't make in the outer envelopes of stellar debris, et cetera. It has to be made deep in the central cores of stars, so it's intimately related to stellar death. Yeah.
Does the sun have a typical metallicity for other stars?
It like Vega in how it defines that the magnitude system is 0. The metallicity of the sun is defined to be 0. Now, the sun is essentially a population 1 star, right? So it has a lot of metals in it. There are actually quite a large number of stars that have more metals than the sun, but the vast majority of stars within our own galaxy, and then as you go to other galaxies, have lower metallicities than the sun. That is less than 0. So the sun is semi-special in that case. But certainly you can find plenty of examples where the metallicity is +1. You can't really find examples of metallicity being something much larger than +1, which means it has 10 times as many iron atoms per hydrogen atom. But you can certainly find systems that have much, much less iron relative to hydrogen. And in fact, one of the colloquia that we had a few weeks ago from Anna Friebel, who's actually Mariska Creek's office mate at Harvard, she looks for these very, very low metallicity stars, because if you're looking at those stars, you're basically looking at these very old stars that have been around for a long time and haven't been enriched by sort of the full chemical cycles of the universe. They were actually just enriched very, very early on. So some of these stars, because they have uranium in them, they have other radioactive elements, you can actually date those stars, and you wind up getting, because you look at the different ratios, you wind up getting ages of those stars, which is basically the age of the universe. Yeah. Okay. And then in thinking about population 1, population 2, and population 3 stars, you also saw the differences between open clusters and globular clusters. And then remember that globular clusters are almost entirely inhabited by old stars, likely mostly population 2 stars. And open clusters are almost by definition population 1 stars. There isn't a hard and fast cutoff between age and metallicity between the population 1 and population 2. That the population 1, population 2 is really something that's around solar is a population 1. Something much less than solar would be a population 2. And then location is also very important. If it's in the disk and it looks to be a fairly young star, it's almost certainly population 1. If it's out of the disk and it's old and red and low mass, it's almost certainly population 2. Okay, so any questions about what you did last time? You nailed it. You get it. You get a gold star. 2 gold stars. All right, so we're interested in understanding the distribution of stars and mass within the Milky Way, and that's sort of the subject of today's lecture. You can look within the local volume of around the sun, and this is sort of a depiction of all the stars in that local volume, moving out only in very small increments of distance. And what you see up there is sort of the typical scale of just 100 light years. And you can see some of the famous, very bright stars. Here's Vega, for instance, actually quite close to us. This would be us looking in towards the galactic center. So this is L of 0 in galactic-centric units, and B of 0 also by definition. If you look anti-center, you're looking at 180 degrees away. That's L of 180. It's still B of 0, right? Just trying to have you remember coordinates. And then all these different stars are going to wind up being at different positions along this plane. This plane that you see right here in blue is the galactic plane, essentially. What else is there to take away? Oh, yeah, if you're reading this, all the dotted lines are the ones that are below the plane, and all the straight lines are the ones above the plane. And so this is a way of depicting sort of a 3D volume by actually having these lines be a line that's the height is sort of consistent with the distance above this plane. Okay, so we'd love to count all these stars because that would give us a sense of the mass distribution around us in the local universe. This is a picture or table, I guess, from Wikipedia of the nearest stars to the sun. There's a large number of people who actually, well, there's a subset of astronomers who like to find stars near the sun because you can imagine you study them very well, and you could actually even image around them to potentially look for exoplanets, etc. The nearest star to the Earth, of course, is the sun, and then after that is Alpha Centauri, which is actually a distribution of 3 stars. But you just keep on going farther and farther down. What you notice is that in units of parallax, that number goes farther and farther down because they're ordering this in order of increasing distance away from us, which is this column right here. And you can see the uncertainties in these numbers. We know the distances to these stars very, very accurately. And those distances and the accuracy of those distances are only improving with time. I don't know what else to say. Oh, you can see a nice sort of compilation of the absolute magnitude. Remember, this is why we have to do magnitudes, because I have to show you these tables, because this is what's actually quite instructive. And remember what it is for the sun, 4.85 in whatever units the Wikipedians decided to put it in. And you notice that most of these numbers are much higher than that. So most of the stars that we know about within our local universe, very, very local universe, are actually much fainter than the sun. And the different stellar types of these are all up here. The sun is a G star, and there's actually, the Alpha Centauri A, which is what we've always thought of as Alpha Centauri, is actually a fairly close analog to the sun. But most of the other stars around us, this one aside, Sirius, which I've talked about before, are all very low mass stars. They're all basically M stars, and this is color coded with their approximate temperature. So most of them are fairly red. Yes? That's a good question. If you find a new local star, you'll name it what you want to, but I think the International Astronomical Union will eventually get to weigh in on that because it's so important. I mean, if you go out with a telescope or you go online and you sort of download a random image of the sky and you see a star, there's like a vastly good chance that no one's ever actually thought about that star before. So you could just name it, and you could give it to your family and say, here's a cheap present for you, and no one would actually, would get mad at you. A lot of these have historical meanings behind them, and many of the stars that we know about actually come from sort of Arabic astronomers. Many of the stars are actually sort of given a couple of different letters in front of the constellation name. So this is related to their sort of brightness within the constellation. Some of them, like Barnard's star, was actually discovered by someone named Barnard. So there's actually, the answer is it's quite a heterogeneous set of nomenclature for the nearest by stars. And then stars that are much, much further away are usually things that are pretty boring. Like if you're doing a survey of Cepheid variable stars in the Large Magellanic Cloud, and you find one of them, you call it, Cepheid LMC, number 1.
So what is the 359 and Wolf 359 star?
I don't know.
Is it a Wolf-Rayet star?
No. It's not a Wolf-Rayet star. Probably discovered by someone named Wolf. I don't know, maybe some wolf cried up at that part of the slide. And you can see also that a number of them have alternate names, right? So many of these things, and in fact, you can go online to this website called Sinbad, and you can type in the position, or you can type in one of these names, and it gives you all the other common names for this, right? So if you have a catalog of stars, you can call it whatever you want, and then you publish this, and it says, oh yeah, you just published some information about a star which we already know is Ross 154. Usually if you have a V in front of it, it's actually a known variable star. But it's a crazy convention. Yeah.
What's a DA star?
This is a sort of designation of a type of white dwarf. So there's different types of white dwarfs depending on what their chemical compositions are. Okay, anyway, that was... So the idea, of course, is that we want to actually study these stars. We want to understand the number density of stars per, say, parsec cube in our local universe, because that gives us a reasonably good sense of what the number density of stars is perhaps in maybe a larger volume inside of the spiral arm that we happen to be near. But what's interesting about this is if you take all the stars within 5 parsecs of us, and I should lower this a little bit, you can see on the x-axis, this is parallax, going from something which is small to something which is even smaller. So this is increasing order of distance. If you take all of those stars and you say, okay, given those total numbers of stars, right, there's basically only a few dozen of them, within 5 parsecs, that gives you a nominal guess at what you think the number density of stars is per unit volume. If you then project that out to something only around 25 parsecs, so only a factor of 5 farther out, what you notice is that you're actually missing a large number of stars. There's actually 62% in this plot that I pulled over a year or two ago of stars that are missing from the sample. Now, it could be that we just happen to live in an over-dense region, so we're over-predicting the total numbers of stars. But very likely, it means that we're just not able to identify these stars, which is amazing, right? We're talking about studying galaxies on the other side of the observable universe and learning something very interesting about the physics of how those galaxies operate. And within our own local neighborhood, we actually are missing a large part. More than half of the stars are essentially missing. And that's because most of those stars are incredibly red and incredibly faint. And even with the world's best detectors now, it's quite hard to find them because it's not like they're all in one place on the sky and you can concentrate. They're going to be in random places on the sky, and so you don't actually know where to look. So that's fairly interesting. Do a little bit now about counting stars as a way to understand the distribution of stars within the galaxy. And I think you've done some of this already, but I'll just sort of repeat it. The idea here is that if you're going to count stars, you've got your little you've got your little telescope, and you're going to look in some sort of region on the sky. The idea is to extend what it is that you learn about this little patch on the sky to the whole sky itself. This is what's called the field of view. F little o capital V. And more or less it's the sort of the total size of the sky that you wind up observing. This is also called omega, large omega, capital omega, which you'll hear a lot of people call it a solid angle. This sort of solid angle is more or less the fraction of the celestial sphere that you wind up taking up. So if I take up just this little patch here, I could count up how many more patches I need to cover the entire celestial sphere. This capital omega of the whole sky has a total quantity of 4 pi stir radians. A stir radian is basically radians squared, but it's in angular terms. And this is this number of 4 pi, of course, comes from integrating basically the unit sphere, 0 to 2 pi, 0 to pi of r squared sine theta d theta d phi. This is equal to 4 pi r squared. And if we're talking about the unit sphere, we just say r is equal to 1. So that's where the 4 pi comes from. Let's see. What is this in units of degrees squared, right? Because I can just look at a small patch of the sky. I can sort of figure out the total size and say, oh, that's twice the size of the full moon. Full moon is half a degree. So if I'm subtending that amount, then I can just sort of work out the numbers and come up with degrees squared. And I want to be able to convert back and forth between stir radians and degrees. The way to do that, of course, is that if you have 180 degrees, that's pi radians. If I now have to do this in 2 dimensions, 180 degrees divided by pi, and this gives us times 4 pi to get the full sky. This is 41,252 degrees squared. Right? So right away now, if you know that you want to survey the whole sky and you want to do it in a certain amount of time and your detector and your field of view takes up this amount of square degrees, you can figure this out very quickly. Of course, from any one site on the Earth, you're not able to see the entire sky, right? You can only see, certainly at nighttime, a small fraction of that. Maybe 1/4 of the sky or 1/3 of the sky is available at any one time. So you're talking about only 10,000 square degrees. Anyway, it's sort of a useful number to know. So if we want to now count stars, the number of stars out to a distance d, which is brighter than a magnitude which I'll call m prime, and stars is just going to be equal to the volume that I probe times the number density of stars that satisfy this criteria. I said less than m prime because we want to find all the stars brighter than a certain magnitude level. This is equal to the total field of view that I wind up covering divided by 4 pi. So this is the fraction of the total sky that I wind up observing times just 4 pi over 3 d cubed times this n stars less than m prime. So this is the entire volume. And this is just the fraction of the sky observed. n stars, just so you have it in your notes, is going to be units of parsecs to the -3, because we're talking about a volumetric number, and obviously the volume is going to be in units of parsecs cubed, so that makes sure that this is a dimensionless quantity right here. So now to find d for a given m prime and big M, absolute magnitude, we know that m prime minus capital M is just 5 log of d divided by 10 parsecs. If I put d in units of parsecs, then this is just 5 log, and I'll call it d parsec minus 5. So now I can solve for d in units of these other quantities right here, and I see that d is less than 10 to the little m prime plus 5 minus m all divided by 5. This is 10 raised to this right here. Okay? So what is this saying? If I have some magnitude limit of my detector, so I'm only able to see to 18th magnitude or 20th magnitude, and for a given absolute magnitude of those stars that I might be looking at, I can now tell you out to what distance I'm observing. So I can plug this back in here, right? So I'm plugging this number back into this quantity over here, and I wind up getting n m less than m prime, so brighter than some magnitude threshold, is just the solid angle divided by 3, n star 10 to the 3/5 m prime plus m. 3/5 plus 5 minus capital M. So this is actually kind of interesting. It means that if I want to now make a plot of the distribution of stars as a function of limiting magnitude, now let me take the log of big N as a function of limiting magnitude. And so I'll go fainter in this direction here. So increase m, fainter. You can see that if I take the log over here, so I'm going to take the log of this quantity here, I'm going to take the log of this quantity here, there's going to be a bunch of constants, but it's going to go something like 3/5 times m prime. So this should just go like this, with the slope of 3/5. So you think this is what we observe? No? Why are you shaking your head? Because I asked the leading question? Yeah, right. Dust. Well, I already told you that we don't observe it, and that's because, as you go to larger and larger distances, we're actually sort of not seeing the very faintest stars. But that was in sort of what we would call a volume-limited sense. So where we actually said, let's just fix D, and I'm going to find all those stars, no matter how faint they are, within that D. This is a little bit different. This is saying, given that I basically have a detector which is capable of going to some sort of m prime in apparent magnitude, what do I see? And of course, you're going to wind up seeing a conglomeration. This is, by the way, this is for a fixed capital M, right? So this is treating this capital M as constant. I just showed you also that capital M is not constant. All the stars within our local volume have a large distribution of what their absolute magnitudes are. So for a fixed capital M, I should, qualify it. For a fixed capital M, this is what I see. So this is a little bit different than the local universe, but you're absolutely right. What happens is that you actually see this work very well, and then eventually you see this wind up sort of tailing off because of dust. It's actually a pretty terrible way of making measurements of the number density of stars as a function of magnitude. The other thing that's probably, I think, most interesting, because if I'm going to take a picture of the sky, I'm going to see stars which are both faint intrinsically and close by, and stars which are very bright intrinsically and far away. What I really want to know, if I just count those stars, what are the total numbers I'm going to wind up seeing within, given that I might have some guess of what this number density of stars is in the local universe. So to do that, you want to integrate over all big M. So n less than m prime for all big M is just going to be the integral from minus infinity, saying that there's sort of the brightest star in the universe or something, right, down to capital or big infinity, not minus. I don't know what capital infinity means. Times the number density of stars as a function of capital M times this quantity omega divided by 3, 10 to the 3/5 m prime minus 5 minus m. There should be a plus here. Yeah, plus 5, excuse me. dm. So this is the number of stars per unit volume per unit magnitude. So the number of stars basically between m and dm. So that's some sort of distribution. We already know that this distribution has some sort of shape to it. It's not that at every absolute magnitude bin between m and dm there is an equal amount of stars. Something that you've seen before if you took 7a is that this quantity n of big M as a function of big M looks like what? Does anyone remember? First of all, are there more very small m's, bright stars, versus very big m's, very faint stars? No. It goes the other way around, right? So for every really bright big star, say an O star, an A star, or B star, you have many more of the fainter stars and the redder stars. So if M is increasing in this direction here, that's towards fainter, right? Because this is a stupid magnitude system. That means that we have to have some sort of slope like this. And in fact, it probably tails off somewhere around here. We don't know exactly where the cutoff is, or if indeed there is a very hard cutoff. But something around 0.08 solar masses is where things cut off. This is sometimes what's called the initial mass function. And actually, this would be the log of that number, just so it would be a straight, because this is probably a power law. And the sun is somewhere out here. Anyway, so this is some sort of functional form, which I won't have to tell you right here. I can take out a large number of these terms here and make my integral a little bit easier to evaluate and see. This is omega divided by 3, 10 to the 3/5. I can take the m prime out because that's just the number that's constant for the purpose of this integral. M prime plus 5 minus infinity to infinity, 10 to the minus big M times, actually 3/5 big M times n of m dm. This obviously is sort of a finite quantity in the sense that we can't go to arbitrarily high magnitudes, because then we'd start getting into like the brightness of a light bulb, right? Or the brightness of a planet. Eventually, we're going to cut it off, and the definition of a planet versus a star, you might say, is that a star actually makes its own heat through processes that aren't just involved with gravitational collapse. That is, they undergo nuclear fusion at some point in their life cycle, and that number cuts off somewhere a little bit below 0.08 solar masses. Anyway, this is probably dropping off for stars very rapidly. We don't actually know because it's very hard to find and study those stars. So on the bright end, large M end, that's finite. And down here, this is actually a fairly steep power law. And if you put this all this in here, you wind up, even though I'm integrating from minus infinity to infinity, I'm really just integrating over a small amount. And this is a finite quantity. But what's very interesting about this? Think about this term now. And think about my fixed field of view, and think about some sort of ideal detector that was capable of detecting lots and lots and lots of photons. If I have a really big aperture and it's a big light bucket and I can collect lots of photons, is M prime larger or smaller than if I have a really small light bucket? Yeah, this is just related to my flux, right? So if you think of M prime as a flux limit, that flux limit is going to be related to the size of the aperture of the telescope, right? And the quantum efficiency of my detectors for detecting photons and things like that. So as I increase the size of my aperture, I just get better at collecting photons. My magnitude limit of what I can actually see in a finite amount of time will wind up increasing, so I can see fainter and fainter and fainter. That's all that's really saying. Think about it. You've got a camera. You decide to leave the shutter open for a little bit longer, right? You're able to see slightly fainter objects. If I go fainter and fainter and fainter, then this number of stars that I wind up collecting and seeing on my little image of the same part of the sky just keeps on going up. If I had a very, very big telescope and I was still looking at the same field of view of a small part of the sky, I keep on going, and dust issues aside, I just keep on getting more and more because I'm raising 10 to a positive number, right? As M prime keeps on getting larger and larger and larger. I get to 30th magnitude, I get to 40th magnitude, I keep on going. What's really strange about this equation that we've just worked out is that it says that if you have a capable enough detector, there's an infinite number of photons that you could wind up collecting. This is something which is called Olber's paradox. We'll see this again in a cosmological sense, because the way that you solve Olber's paradox is by appealing to the expansion of the universe and the finite age of the universe. But a long time ago, somebody just worked this stuff out, Olber, and realized there's a serious problem here, right? If you just keep on getting fainter and fainter, you wind up seeing more and more stars. Basically, it's saying that we should be seeing an incredibly bright sky everywhere we look. The night sky should actually be incredibly bright. And in fact, what we'll see when we work out this concept of surface brightness in the context of galaxies, you'll wind up seeing that as you wind up taking a given galaxy, or in this case, it would be a star, and you move it farther away, it subtends a smaller field of view on the sky, if you want to think about it that way. Use the word subtend. But its surface brightness, which is more or less the flux per this field of view, remains fixed. So that means that for any little place on the sky, I wind up intersecting some other star. And again, dust issues aside, it means that the entire night sky should be as bright as the sun, which it's clearly not. So how do you wiggle out of Olber's paradox without knowing about cosmology? You just did a Home Alone? Yeah. That's not how you wiggle out of it.
Say that there's not that many stars, or there's a finite number of stars?
Yep. There's a finite number of stars, and then you're done, right? You get out of that. If you live in this homogeneous universe where this n, this little n, where is it here? This little n or this little n is constant, and you just posit that the universe is sort of homogeneous everywhere around you, then you don't run out of stars. It just keeps on going. But if you just think about the Milky Way, the way you wiggle out of Olber's paradox is eventually you just run out of stars. You've gotten so faint, then you've gone basically the faintest star in the entire galaxy, and you've gone to that star at the farthest distance outside of the galaxy. The galaxy has a finite size, effectively, until you start getting into other galaxies. So this is Olber's paradox, and hopefully you see that this is sort of probably not the best way to be making measurements of stellar density within the galaxy, because you're really just counting stars. Fundamentally, you're just counting stars without knowing their distances. So making measurements of distance, as it turns out, is obviously the way to go about this. By making a measurement of the distance of stars within some sort of finite volume, you could just sort of take a collection of stars out there, and if you know their distances, then you can wind up inferring what this n of big M is, and you can wind up figuring out what that is at that place, a kiloparsec away from you in the galaxy. So that's actually how we build up a sense of the distribution of density of stars within the galaxy. Remember, we've talked about parallax. Are there any questions about that before we move on to making measurements of distance? Everyone's got that? Okay. I'll just erase that. We've obviously already talked about parallax. Measuring distance in the galaxy isn't just about making measurements of the total numbers of stars, right? It's making a measurement of the total numbers of stars in different places in the galaxy, which is our way of building up our understanding of what the Milky Way actually looks like, right? Unfortunately, we can't get out of the Milky Way and look back down on it to look at whatever structures are happening in the center of the Milky Way. We can't just stand on top of the Milky Way and look down and just sort of count stars. We're embedded in this thing with dust and gas, and so it's actually quite hard to do this from our vantage point. But understanding the overall size of the Milky Way, and as we'll see probably at the end of the lecture today, understanding the mass of the Milky Way depends very critically on us understanding the overall distances to major structures, like the nearest spiral arm, like the galactic center. Parallax, at least for the next few years, is something that is really only restricted to our local universe. It's sometimes called capital pi. This is 1 arcsecond for a distance at 1 parsec. And as I increase the distance, this number winds up going down. This is using the motion of the Earth, and it's just a purely geometric way of making measurements of distance. There's something else. This really gets us out, again, for a while, only to about 100 parsecs. There's a couple of specialized techniques on certain types of stars, particularly ones that are emitting at radio wavebands, where you can actually make very, very precise measurements beyond this. But this is a pretty limited volume, given that the distance between us and the galactic center is 8 kiloparsecs. That's sort of the D-limit, if you want to consider it. This D-limit, by the way, with a satellite called Gaia, which is launching next year, will actually increase to something like a few kiloparsecs, call it 5 kiloparsecs. So pretty soon we're going to get a vastly bigger volume out to which we can make geometric measurements of distance to stars. Yeah. D-limit is sort of the limit out to which we can make a significant measurement of parallax. So I could take a star, and if it's within this volume, defined by this limiting distance, then I can know its distance to a high level of accuracy. Outside of that, it's harder and harder to do that. And with Gaia, we're going to basically get more than an order of magnitude farther away, maybe even 2 orders of magnitude farther away. Yes? No, so the nice thing about this is purely geometry, right? And so in principle, you can make a parallactic measurement out to another galaxy if you had the ability to sort of see how the galaxy appears to wobble with respect to even further distant galaxies. No one's ever done that, and it'll be decades probably before we can do that. It's basically a technology thing, which is wrapped up or convolved with a very difficult to overcome, if not impossible to overcome, sort of optics issue. The fact that you need a very large diameter to make a measurement of a very precise position on the sky. And the precision basically scales inversely with the size of your size of your diameter. So if I want to make a precision measurement of the location of a star today and do it again 6 months from now when the Earth is on the other side of the sun, and I want to see how much that wobbled, I would need to do this with a very, very large aperture. Or I need to do it very, very short wavelengths, as it turns out. So this is called the diffraction limit. So the technology couples into that, and that until we have the ability to make these very precise measurements with very large apertures, we're going to be limited to sort of these types of volumes. That's a good question. Okay, so this is changing, sort of 2012, 2013, we'll start getting some really interesting measurements to much more distant sources. Yeah?
What is it about that will allow it to measure?
So it's a bigger aperture than has been used before. That's one thing. So they're able to just push because of that. But also they're able to capture the light and have sort of very precision. It's a satellite. It'll be launched by the European Space Agency, next year or something, and start producing measurements a year later. It's just going to be a very precise experiment where they're making sure that they've got all the systematic uncertainties that come into dealing with this in space under control. Any other questions? Right, okay, so we need another technique to get beyond sort of this 100 parsecs, and the typical one used is something called kinematic parallax. And kinematic parallax basically or statistical parallax is a way of using an ensemble of stars and use a special property, also just really appealing to the geometry of the problem, to come up with an average distance. So here what you do is, the idea behind kinematic parallax is you start off with some sort of star cluster. So the easiest thing to think of is perhaps a globular cluster, an open cluster, whose distance you wind up inferring are all about the same from us, right? So if I have a globular cluster at a kiloparsec, and I just see this swarm of red stars all in this very small place on the sky, I can be rest assured that almost all of them are going to be at about the same distance from us, right? Because it's a gravitationally bound system. Now that gravitationally bound system is going to, if it's not expanding or contracting, is going to satisfy the virial theorem, which means that there's an overall gravitational potential associated with that system, which means that there's an overall sort of velocity associated with each one of these stars that's part of that system. Right, so these stars are going to have a typical internal velocity associated with them. Again, think of a globular cluster, if you haven't heard this already, as sort of a swarm of bees, right? You sort of have this gravitationally bound system, and all these little red stars are kind of all moving around in this potential. That ball of bees is itself moving around the Milky Way. And we're moving around the Milky Way in our own way, right? We have some sort of velocity in some direction. And then this star cluster over here has some overall velocity maybe going in another direction. But as viewed by us on the sky, we can see the radial velocity very easily of each one of these stars. That is, how fast towards us or away from us those stars are moving. How do we do that? Doppler shift. Take a spectrum. You see that these characteristic lines are not as where they are in the laboratory. Some of those stars might be moving a little bit towards us. Some might be moving away. But on average, they're going to have some overall radial velocity towards us or away from us. How would we tell what the sort of velocities are in the other directions? Not towards us, away from us, but this way on the sky. Sort of. No. Just watching it, yeah. So parallax is just watching it as well, but parallax is watching it do something specific, wobble back and forth with a year period because of the Earth's motion. But even if we can't measure parallax out to 10 parsecs, we certainly can see things just sort of moving along on the sky, right? So something which is nearby, which has a proper motion that's basically doing this on the sky, if it's nearby, might actually look like this. And then if it's a little bit further away, the amplitude of that variation might be less, and as you go really far away. So this might be 100 parsecs, this might be 300 parsecs, and this might be 1 kiloparsec. So all I have to do is take a measurement to measure parallax. I have to do this, every 6 months and make these measurements, right? But to measure proper motion, I have to see where it was in 1950 and see where it is today. And I've got a proper motion of that one star. So if I sort of draw this view much further away than what we would draw if we're doing parallax, here's us sort of around the sun. Here's a star cluster. Relative to the motion of the sun around the galaxy, each one of these stars is going to be moving more or less in the same direction towards us or away from us. And now I've written it as being away from us. If I zoom into one of these vectors here, this might be the velocity vector of that one star. In this direction, we would call this the radial velocity. And in this direction, we would call this the tangential velocity. The radial velocity of this star is something that I can measure. We just said that. The tangential velocity is the same as saying proper motion. Well, proper motion is usually given in arc seconds per year. But this is, VT is related to proper motion. It turns out that if you actually view this star cluster moving on the sky, and you look at where the velocity vectors are all heading, so now you're not looking at this radial velocity, just the tangential velocity. It'll look like an ensemble of stars in different places, slightly different places on the sky, all moving in some direction. And on the celestial sphere, it looks like it's moving towards something called the convergent point. This is a better depiction of what I was just trying to draw. I think this is also in your book. That's basically what I just showed you before. Here's the convergent point. There's an angle between where the star cluster is and where all the velocity vectors appear to be pointing. And what's very strange is that even though you've got this cluster of stars that are all at the same distance from us, or basically about all at the same distance from us, and they're all basically moving on mass, except for the fact that some of them have internal motions with respect to the bulk mass of the gravitational bound system that they're a part of. It actually looks like, instead of them all being parallel on the sky, it looks like they're all sort of pointing towards one position on the sky. Does anyone know what these are called? What? Clouds? Oh, no, I meant this stuff. Do you think the sun is actually like, a mile above the cloud? No, that's what sort of your eye is telling you. This is an optical illusion. These lines that you see right here are actually all parallel. But for something that's far away from us, when you see parallel lines, it actually looks to be convergent. These are called crepuscular rays. That's probably easier seen like this. So in a farm, you've got lines which are actually parallel to each other, or almost exactly parallel. But it looks like it's all converging to a single point far away. This is what we see on the sky when we look at star clusters. It looks like they're all moving towards a certain point. So we can work out the mathematics of that, and what's interesting is doing that mathematics, you can actually get a distance to that star cluster. VT is just VR times tan of this angle, which I'll call phi. If I define something which is called mu, which is the proper motion, this is just vt divided by the distance to that object. And you can put this in units of arc seconds per year. Why is that? Hold on one sec. Why is that? Because this is units of distance divided by time. This is units of distance. So I really have units of 1 over time. 1 over time is the same as radians over time. I can turn radians into arc seconds. Yeah. If it was only in the transverse direction, yes, you would. It has nothing to do with the radial direction velocity. The radial velocity direction was 0, it would still work. But if you only had radial velocity, you wouldn't see that. You wouldn't be able to measure it because they'd all look like they're just all moving away from you, right? So those velocity vectors that you saw projected on the sky would all be 0. Yes?
Can you repeat what mu was?
Yes, this is called proper motion. And how you actually measure it is like this. You take an image of that part of the sky at one time, and you come back years later if you want to, and you see how that star moved. And this motion is some sort of angular distance, which we'll call theta, and proper motion is just theta divided by the total time it took in years to make that measurement. Now, any one of these stars, I could apply this formula. And I would wind up getting an effective distance. But what you see is the way that people make these measurements, is that you'd use an average over all the distances inferred for all the stars. And this is usually the average of the radial velocity, tan phi, divided by the average of the proper motion of all those stars. It's not 100% clear whether it makes sense to take the average of d, which is basically the average of this entire quantity per star, or whether you average each of these radial velocities and average each of these proper motions and get it. Doesn't really matter for our purposes. But the point is that you have to average because each one of those stars has a slightly different velocity with respect to all the other stars, and they're not exactly pointing at exactly the same convergent point. So you have to do all this stuff sort of in an ensemble sense. And it turns out if you do the units right, the distance in units of parsecs is equal to the average of the radial velocity tan phi divided by 4.74 times the average of the proper motion in arc seconds per year. And this is where VR is in units of kilometers a second. So that's a kinematic parallax, and kinematics give you the sense of motion, right? So it's the origin of the term. This is actually quite powerful. I have a cluster of stars. I believe them to be bound. If they're all sort of converging towards a single point, I can wind up figuring out the distance to that cluster. Kind of cute. And that's basically pure geometry, right? Just like parallaxes. There's really not appealing to any sort of physics of stars or anything like that. Now, this gets us out to distances of maybe a few kiloparsecs. Yes, you had a question.
Also, is there another way to find the average proper motion without? Because it seems like we can find the average distance in terms of the average proper motion, but according to the formula we wrote before that, it seems like you can find the average proper motion without previously knowing the average distance.
That's right.
So is there another way to find the average proper motion without using the distance?
No. The point is you use those two equations use these two equations and you solve for distance. That's all that is. It's just solving for distance. Proper motion is something that's measurable. This is measurable. This is measurable, and this is measurable. So what you're doing is basically eliminating the tangential velocity from the two equations, solving for d. Okay. So what's interesting, of course, is that even for systems of stars whose proper motions you can't measure very accurately, there's other ways of making measurements of distances to those objects. And one of those, sort of the next sort of farthest out, is something called main sequence fitting. I won't go into great detail here, but essentially this is looking at the main sequence of a star cluster, say a globular cluster in this case, and looking at where there's a turnoff in that whole main sequence. So you remember turnoff is sort of related to age. I can fit the main sequence, assuming that this number density of stars as a function of absolute magnitude is more or less constant for different star clusters. I can fit the age of that cluster just by looking at where that turnoff is and using some of the knowledge that I have about stellar lifetimes. But also, just by looking at the ensemble of that entire system, I can more or less figure out what the distance modulus is, because there's going to be an overall offset between, say, a main sequence set of stars that are nearby, maybe within my parallactic volume or within my kinematic parallactic volume, whose distances I know very well, and something farther away. I may just look at that offset and look at the difference between the apparent magnitude of that system and the apparent magnitude of another system. And then what I'm really just doing is leapfrogging, right? I'm just sort of figuring out the distance of some objects here. I'm looking at the apparent magnitudes of the main sequence. And then I go to some other system and I look at the apparent magnitudes there. So just to illustrate this, if I have B minus V, and let's say I have V, remember V is short script or long script for little mv. Main sequence looks something like this. This is the main sequence. This is what's called the turnoff mass or turnoff magnitude. And let's say I do this for a star system whose distance I know from one of these two techniques. So I know what this distance is, right? Okay. Now I look at some star system which is farther away, and I look at its main sequence, and maybe it looks something like this. It's this distance here, right? This is just sort of m of a distant cluster minus m of a nearby cluster. And that's going to wind up giving my relative distance between the distant one and the nearby one. Right? That's all that is. And you need to do main sequence fitting. You need a large ensemble of stars, because any one star, remember this is sort of all very fuzzy, right? You need a large ensemble of stars to figure out precisely what that distance is from here to here. And again, dust is an issue, because dust is going to wind up affecting my apparent magnitude. And so there you have to play more games and try to infer how much dust you have by looking at how much more red the whole main sequence appears to be. So main sequence fitting really kind of gets us out into large distances. This is something you can do throughout the galaxy. But the objects that are used most often in sort of understanding the overall size structure of the Milky Way and actually getting us to distances beyond the Milky Way are things called pulsational variables. And in particular, there's two types of pulsational variables, those called R. Lyrae and another called Cepheids. Give you a couple of slides on that now. The key here with R. Lyrae stars and Cepheids is that they not only pulsate, so they're getting, when you say pulsate, they actually appear to get brighter and fainter on sort of human time scales. Everything's changing on long time scales. The sun is going to be changing its luminosity quite dramatically if you wait sort of a few billion years. But on actually sort of less than day time scales, our Lyrae can change their brightness by basically 100%. And Cepheids on week-long time scales can change their brightness tremendously. We know about Cepheids and our Lyrae throughout the Milky Way, but in globular clusters, these auroral Lyrae have been studied quite well. If you have an auroral Lyrae within some sort of parallax distance, you can make a measurement of its absolute magnitude. If you then look at another auroral Lyrae and you understand the relationship between pulsations and overall luminosity, you can make measurements of distance. So this is something that Harlow Shapley studied in sort of 1915. And he saw these things in globular clusters and studied the distances to those globular clusters. And he was quite famous for doing that. And what he surmised, quite interestingly, if you just look at the positions of globular clusters on the sky, he surmised that most of the globular clusters appeared to be clustered around Sagittarius, the constellation Sagittarius. So you look at it in all these different places, and all these old clusters of stars appeared to be very congregated towards that direction. And because he had a way of making measurements of these distances, and I'll tell you more about our Lyrae in particular when we talk about the overall distance ladder of the overall size scale of the universe. But that itself has a very interesting history. You can actually then start figuring out how far away the sun is from that distribution. Think about it this way. If you're sort of standing in a field and you see a bunch of fireflies all sort of congregating over in that direction, and you know the distances to a few of those, and you assume that the center of the universe or the center of your galaxy is where those things are centered, you can then figure out your distance from that overall center, right? So what he did is he tried to make measurements of these distances, and he figured out that the sun is not at the center of that distribution. I mean, first of all, take a step back and note that it's been less than 100 years that we've actually understood that the entire universe wasn't just the Milky Way. 100 years ago, people basically assumed that the universe was the Milky Way. And so people around the turn of the last century were trying to understand truly the size structure of the Milky Way and truly understand all the different constituents of that. So one of the great breakthroughs was understanding, indeed, that the sun wasn't at the center of the Milky Way. Right? We had no other way of knowing that. We've already said that counting stars is sort of a pretty terrible thing to do, but this is what had been done for a number of years. Herschel and his sister Caroline made measurements of the sort of total numbers of stars in something like, how many different directions? 683 different directions. And he did this in 1785. So he knew sort of, and they knew what the overall sort of densities were around them. Of course, they didn't know about dust. So they weren't able to get sort of that great picture. But this fundamental question around the turn of the century was, what are these nebulae? We understood sort of the overall, or at least that we weren't in the center, or many people believe that we were in the center. But there were lots of weird things out there that people knew of. These are called planetary nebulae, because if you take a picture of this with a sort of not high-quality telescope, it basically looks like the overall size of a planet. Actually, Herschel made this mistake. But we know now that, of course, this is the last gas of a star as it's expelling its outer envelopes and on its way to becoming just a cooling white dwarf, which is the thing that's illuminating from the inside. How is that different physically from whatever this thing is? This looks like some sort of reflection nebula. How is that different from this thing here, which if you sort of blur your eyes, they don't look qualitatively, They don't qualitatively look all that different. So people debated what are these nebulae, and in particular, what are these spiral nebulae? People had no idea around the turn of the century what these things were. So there was actually a great debate in the astronomy community over what the overall size of the universe was. And it turns out that Shapley was on this sort of one side of this debate, believing that we were not at the center of the universe through his R-Lyrae measurements with globular clusters. And there are other people saying that, no, we're probably near the center of the universe, but the universe isn't just our universe, it's other universes, that these spiral nebulae are other, what are called island universes. So they had a big fight. They just slugged it out. No, actually, they had a debate. It was a talking debate in 1920, a very famous, what's now called the Great Debate, between Curtis and Shapley. Shapley was working at Mount Wilson at the time. He later, right after this debate, became director of Harvard College Observatory. And Curtis, at the time, was working at Lick Observatory and did most of his work at Lick Observatory. They had different views, and so what they did is they basically, one of them talked for an hour, the other talked for an hour, and they sort of then had some time to sort of rebut each other. And the room in Washington, D.C. was filled, it was in the National History Museum, was filled up with all the sort of cognoscenti to making sort of an educated guess over what this answer was. And they each had their own sort of pieces of evidence. So on Curtis's side said that spiral nebulae were galaxies like our own, and that those are what at the time were called island universes, and that the sun is very near the center of our own galaxy. Shapley argued that the spiral nebulae are actually in our own galaxy, and that the sun is very far from the center. And what's interesting is that Shapley was being fed by some observations, very recent observations, like in 1919, by one of his friends named von Manen. And what von Manen had done is look at what's called the pinwheel galaxy, as we call it today, and looked at the spiral structure and saw over time that the spiral arms appeared to be moving. If they are indeed moving, and you see something that's very far away moving, you know that it can't be that far away, because then otherwise you can work out how that this would be moving faster than the speed of light. It turns out that those sets of observations were basically wrong. And Curtis said if those observations are right, then he must be wrong about his idea that these other spiral things are actually other galaxies that are very, very far away. So the way, and it's a very interesting history, because there's also things called novae, which were, we had known about for a century or so and studied very well. We knew the typical distances to those novae, and there appear to be novae happening more commonly in these spiral things. And so that's one of the arguments that Curtis had, that these things were actually not just sort of nebulae within our own galaxy, but actually galaxies themselves. Anyway, one of the great discoveries that Hubble brought to us was in 1923. We discovered some of these pulsating variables, the so-called Cepheids, in Andromeda, which is the nearest very large Milky Way-like galaxy to us. It's a spiral galaxy. And based on the measurements that we had of Cepheids within our own galaxy, he could then surmise the fact that these Cepheids were indeed very, very far away. And he estimated a distance of 2.4 million light years, which turns out not to be right, but the fact is it was very, very far away. So, there was a debate. There was lots of evidence. People sort of were weighing the evidence in 1920. And then very quickly, 3 years later, this debate was essentially settled. So Curtis had it right that that these spiral things are galaxies like our own, and Shapley had it right that the sun is actually far from the center. Any questions about that? Okay. Without going into then the sort of whole history of how we build up the overall size structure of the Milky Way, I'll just tell you now what the distribution of stars is within the Milky Way. And there's actually kind of a reasonably nice functional form for that. But hopefully it's clear to you all how we might go about doing that in an exercise where we want to actually find out what the distribution and density of stars are within a certain magnitude range in a certain part of the galaxy. If I define and actually draw the galaxy out like this, if I define a distance from the center of the galaxy as capital R, and I define the distance off the plane as z, so think of this as cylindrical coordinates, not spherical coordinates, the number density of stars as a function of z and r is equal to some sort of overall scale, n0, e to the minus z divided by what I'll call z thick, plus 0.085 e to the minus z divided by something called, oh sorry, this is thin. First one's thin, the next one's thick. And all of this is times the quantity e to the minus r divided by something called HR. All right, so let's ignore this part for a second here. This says that as I go above, or actually below, we can take this as an absolute value, above or below the plane of the Milky Way, I have an exponential drop-off in the overall number of stars. And there's two sort of characteristic drop-offs here. There's something called the thin disk and the thick disk. And these are sort of two overall characteristic scales of this drop-off. Z thick is something like 1 kiloparsec. Z thin is something like 350 parsecs. And Z thin is basically where the population 1 stars all reside, and Z thick is sort of a thicker distribution or more puffed up distribution, but much fewer stars. So there's only 9% of the disk is the thick disk stars, and the rest is in the thin disk. That's how we understand this Z dependence. And then this R dependence is that as I go farther out from the center of the galaxy, there's an exponential drop off in the total numbers of stars. And it's going to have that sort of characteristic scale where HR is something like 2.25 kiloparsecs.
Is that like the part on top times the bottom part?
Yeah, it's times. It's the part on the top times the bottom part. So that means anywhere I go in Z and R, I can tell you what the overall density of stars is if I tell you what N0 is. N0, I'll write over here. N0 is equal to 0.02 stars per parsec cubed between the magnitude range of the sun and something about 100 times fainter than that. So you take the sun, you take all the stars that are 100 times fainter, this is this overall scaling. But of course, depending on exactly where we are, and you could come up with basically our location here is more or less around 0. Z is not exactly 0. We're not exactly in the plane of the Milky Way. But I told you what R is. You can see how the density of stars is higher or lower depending upon where you are relative to where the sun is relative to the center of the galaxy. So if you integrate this basically out to all Z and all R, the Milky Way total number of stars is something like 200 billion in round numbers. And the mass in stars is about 90 billion solar masses. So the average mass is something about 40% that of the sun. So the sun is a little bit more massive than sort of the average mass of stars. By total number, the lowest mass stars completely dominate. But this is pretty amazing that we actually know this. 100 years ago, no way, right? Even 50 years ago, there was enough uncertainty about the overall size structure that we didn't even know what some of these numbers were. And now we're sort of getting to those numbers fairly accurately. Yes.
What does E to the bar stand? I mean, besides the number of what is it
It's just this. It's what you might call as the scale height or the scale size of the distribution of stars. And of course, this can't be exactly right because we have spiral arms, and there's a higher density of stars in spiral arms than there are outside of spiral arms. This is an ensemble average over the whole galaxy. All right. So I think, let's see. I think I'll leave it with that, and then what we'll do on Tuesday is pick up with a dynamical measure of mass. So we have now a way of basically making a measurement of the total mass in stars. We basically started off 2 weeks ago talking about the interstellar medium, and I told you that the interstellar medium constituted about 10% to maybe up to 20% of the total mass of stars. What we'll do on Tuesday is we'll figure out what the mass is of the galaxy, irrespective of the mass of stars. And as you probably know, some of you have been maybe keeping up with the reading, we're heading towards this concept of dark matter, this idea that there's vastly more mass and associated with the Milky Way than we can account for in stars. Have a good weekend.